Hi everyone, welcome back to Chem Story. Today, we're diving into how to synthesize alkynes. There are a few different methods we can use in the lab, but we're going to kick things off with the most classic one, the double elimination reaction. Let's take a closer look and break it all down together. One of the most common ways to make an alkyne is by starting with a dihaloalkane. That's a molecule with two halogen atoms, like bromines, either on the same carbon or on neighboring ones. There are two types we usually deal with: vicinal dihalides, where the halogens are on two adjacent carbons, and geminal dihalides, where both are on the same carbon. In both cases, we use a reaction called dehydrohalogenation, which basically means we're removing a hydrogen and a halogen to form a new bond. In the first step, we take out one equivalent of HX, something like HBr, and that gives us a vinyl halide, which has a double bond in the structure. Here's the key part. If we do that elimination one more time, we can go all the way from a dihalide to an alkyne. So it's a two-step elimination. First, we eliminate one equivalent of HBr and get a vinyl halide. Then we eliminate again from that vinyl halide, and that gives us a carbon-carbon triple bond. And this works for both vicinal and geminal dihalides. As long as you've got two halogens and a strong enough base to pull out both equivalents of HX, you can drive the reaction all the way to form an alkyne. Here's something really important to keep in mind. The type of base you use can actually change the kind of alkyne you end up with. If you go with fused KOH, the reaction usually stops at making an internal alkyne because there's no easily removable proton left at the terminal position. But if you use a stronger base, like sodium amide, NaNH2, in liquid ammonia, that can go one step further. It's strong enough to pull off that last proton from the terminal carbon, letting the reaction go all the way to a terminal alkyne. So the bottom line is, if your goal is to make a terminal alkyne, you need a strong base like NaNH2 to get you there. Let's check out another method. You can actually make alkynes from something called Vicinal tetrahaloalkanes. In this setup, you've got two halogens on each of two neighboring carbons. And when you treat that with zinc and heat, you get a double elimination, kind of like before. But this time, you're removing two full equivalents of dihalide all at once. What you end up with is a terminal alkyne with a triple bond right between those two carbons. Now, this method isn't as common as the one with dihalides, but it's still a handy trick, especially if you're starting from a molecule that's heavily halogenated. And here's a cool one. You can actually make alkynes starting from aldehydes using something called the Corey-Fuchs reaction. Here's how it works. First, you react the aldehyde with CBr4 and triphenylphosphine, or PPH3. That gives you a dibromoalkene intermediate. Then, you treat that with butyllithium, or BULI, which is a really strong base. That triggers a double elimination, and you end up with a terminal alkyne. It's a two-step process, but it's actually super useful because it lets you build alkynes from really simple starting materials, like carbonyl compounds. And just a side note here, you won't always see the Corey-Fuchs reaction in standard textbooks, but it shows up a lot in real lab work. So if you're looking to go a bit deeper, or you're thinking ahead to research settings, this is definitely a reaction worth knowing. All right, that's it for today's lesson on alkyne synthesis. We covered the key methods, looked at how base choice affects the outcome, and even touched on the Corey-Fuchs reaction for those wanting to go a bit deeper. Thanks for watching, and as always, I'll see you in the next Chem Story video.